Yes.
Okay, thanks a lot. So we start this session, and the first speaker is Xu. Just go ahead.
Okay, thank you. My name is Xu Li, and I am very excited to be here to give this talk. And the topic is the positivity in the multi-field EFTs. And this is based on this paper, and I work with Chen Jieyang, Hao Xu, Chen Zhang, and Shuangyong Zhou. And the goal of this project is to derive the positivity bounds. When we integrate all the UV states, we can have a EFT Lagrangian. Then we may ask, can this version coefficient tell arbitrary value? Or what kind of the EFT can have a UV completion? Okay. And the possible answer is if we assume that the UV states satisfy the unitarity, causality, Lorentz symmetry, or the Clausian symmetry, then we can have a set of inequalities that can constrain these version coefficients. And these are called the positivity bounds. Then only the EFT that are allowed by these bounds that can have a UV completion. The people have a hot discussion in the last few years. And we see that this group of people have their very important contribution in this area. And we see Chot and Tolly also give this talk in this meeting. And similar to the talk by Chot, we are focusing on the dimension A coefficients. So for the simplicity, we are consider the 2-2 forward scattering. And the dimension A effects will contribute to the S-square energy dependence. So we are going to consider this quantity in order to get to extract the dimension A effects. And then we will use the optical theorem to get the bounds on this quantity. And this procedure is very similar to the previous talk by Chot, but we are using different methods. And the outline is we first introduce our formula framework, and we will study a scalar EFT as an illustration. And then we will introduce several numerical approaches and mention several examples. The framework is we are focusing on the 2-2 forward scattering. Then we can define a contour integration like this, where the contour will contain a small circle and integration along the real axis. The small circle is divided in the low energy region, so it is calculable with the EFTs. And it will give rise to the left-hand side of this formula, where the IJKL are the particle indexes. And the right-hand side is the contribution from the real axis. The optical theorem will say that, okay, the singularity here can be converted into a summation over the all heavy states X. And here the JL exchange corresponds to the Clausian symmetries, where the X will become to U, so it is a contribution from the singularity of this side. This formula can be shown in this diagram. In order to get a master formula, we can get we can define the MIJKL to be the left-hand side. It is the amplitude from IJ to KL, and we can calculate it with the EFT, and we take the massless limit. So we can get the master formula in this. We can see the left-hand side is a function of the version coefficients. So the next, we are going to explore the construction of the right-hand side in order to get the bounds on the left-hand side. And based on this formula, there already exists an approach called the elastic approach. It is when we let the I equal to K and J equal to L, then this process will become IJ to IJ. And this is exactly the elastic scattering. And in this situation, we know the right-hand side become the positive quantity. And then we can get the bounds like this. But if we consider a more general case, the scattering will become from UV to UV. We define the U and V are the superposition of the elementary particle INJs. So this process will become to the elastic scattering between two superposition states. And again, we can see the right-hand side to be a positive quantity. then we can get a general fall of the elastic bonds. But however, we will know that these bonds are not optimal. It's not the best bonds that we get. And to see why I say this, I think we need to go further. And if we look at this formula in detail, we can have two observations. Firstly, is that we know the MIJKL should be the positive linear combination of the MIJ-MKL plus the MIL-MKJ. This statement means that the MIJKL is a convex cone. Then what is the convex cone? Before I continue, I need to explain it with these simple figures. This is a polyhedron cone that's spanned by 4 edge vectors, A1, A2, A3, and A4. Then we see in the figure that any vectors in the cone can be always written as a positive linear combinations of the AIs. And this cone is denoted by the cone AIs. So we can conclude that our MIJKL is a cone that's spanned by the MIJ, MKL plus the MIL, MKJ. In this simple figure, we also see that the MIJKL is constrained in this cone. So that we say our positivity bonds will arise as the boundary of the cone. But how can we construct the cones? This is the questions. But then this will need our second observations. And we know the X belong to the direct product space of the INJ. Then we can rewrite MPTO from IG to X in this, where C is the CG coefficients. Then our master formula will become this. And we see that again, it is a positive combinations of the P. We define the P as the projectors. It can be obtained by the CG coefficients. So with the projectors, it's able for us to find to construct the cone. Then we can get the bonds. With the projectors approach, we can study several EFT in this paper, and I give their bonds in here and the corresponding cone. We especially note that most of them are consistent with the elastic bonds, but here I give these two bonds cannot be attained by the elastic approach, and they are beyond the elastic. In the next, we are going to show more such type of bonds. Now, so far we can see that our projector approach is very useful, but the question will arise when if we cannot obtain the projectors, then we cannot construct the cone, then we cannot get the bonds. This situation will happen when the series have no symmetries, then we cannot obtain the CG coefficients. Then how can we characterize the bonds? And we provide a solution in this paper is to use a dual property of the cone. And this is what I actually want to tell you in this talk. We define the C star as the dual cone of the C, which will contain the element have a positive inner product with the MPTU in C. So from the definition, we know that the C star should be a cone. And we can directly see that the C star should contain all the possible linear bonds that we need. And the most important thing is we know that these bonds are enough to carry out exactly the C, because there's a hyperplane separation. Theorem says that the dual cone of the C star should be the C. And since our goal is to find the independent bonds, and in the last slides, we know the positivity bonds are equal to a vectors in the dual cone. And it is easy for us to know which vectors is independent in the cone. If we look at the definition, we know the convex cone is closed under the additions and the positive scalar multiplications. So any vectors in the cone, if we can decompose into the other vectors, then it cannot be independent, okay? And there is an extreme array, which is defined as the vectors that cannot be split into the other vectors. It is just like edge vectors in the polyhedral cone. So we know the extreme array should be independent. For us, it's enough to find all extreme arrays in the dual cone. Before we are going to find the dual cone, the extreme array in the dual cone, we firstly want to study the index symmetry of the MIJKL. Firstly, we know that the IK exchange or the KL exchange correspond to the crossing symmetries, where the S and U will exchange. And the IJ exchange plus the KL exchange correspond to the rotation symmetries. And with this index symmetry, we can define a subset S2N24, and we force the amplitude belong to this subspace. And then we can also define the Q follow these symmetries. If we expand the amplitude with the Mij MKL plus MIL MKJ, and then from this formula, we know that the Q should be a positive semi-definite matrix, where the Ij and KL are viewed as the index of the matrix. Then we say, okay, the Q should belong to the intersection of this subset of these two subsets. So what does this intersection look like? I can show it in these simple figures that since we know the positive semi-definite matrix will for a convex cone, it is just an illustration. But the intersection will look like that, okay, this cone is cut by a plane. And this object is called the spectral hadron in math. And we know it is well defined and well studied in math. So we say our ultimate goal is to find the extreme rate of the spectral hadron. To represent the spectral hadron, we let the Qi to be the basis matrix of the space, and the Qs can be represented by its coordinates Si. And we force the Qs to be positive semi-definite matrix, then we can define a spectral hadron. And the question is, how can we judge whether a vector S is at an extreme rate? And this problem have to be solved by this paper. But the proof is non-trivial. So I say maybe we can just accept it as a theorem, where we first let Fs to be a lowest unique phase that contain S, and we let the Ui to be a basis of the null space Qs. Then we can construct a so-called B matrix here. The paper says that, okay, the null space of the B matrix will be exactly the near span of the Fs. So once we know the Fs, then we say the X at the extreme rate, or if and only if the Fs have a dimension 1. Then this statement is equivalent to say that, okay, the rank of the B matrix is n-1. And with this, it's able for us to find the extreme rate. And based the above approach, we can study EFT as an illustration. The EFT will contain two scalar with C2 symmetries, means that the series is invariant on the phi I to the minus phi I. And the relevant operators in dimension A can be always written as this. So we can use these operators to calculate the amplitude 1 by 1 in this and fill them in this matrix, and the C is the CG coefficients. So the red region is 0 because of the C2 symmetries. And with the crossing symmetries, an arbitrary matrix in the dual space can be always parameterized as this. So we can according to the degree of freedom, we can choose their basis here, and then we can rewrite the Q as this. And we force it to be positive semi-definite, we can define a spectral hadron look like this. So from this spectral hadron, we can find two kinds of the extreme rays using the above approach. Then we multiply the extreme ray with the amplitude, then we can find the full bounds. And this is the standard procedure. How can we find the bounds? Yes, I give the bounds here. And to understand this bounds better, we can visualize the Aurora cone of the space, dual space, and the amplitude space. Both of them are the 4-dimensional object, so it's able for us to display their 3-dimensional closed sections. The coordinates of the dual space is A, B, C, and D. So this Aurora region shows that the spectral hadron will look like this cone. And the bounds shows that the Aurora version coefficient space is this cone. And to see that our statement that the extreme rate equal to a positivity bounds is true, we highlight the two kinds of the extreme ray with red and green here. We especially note that these green vertex are corresponding to this phase, and these vertex correspond to this phase, and this curve are corresponding to this phase. And these correspondences are exactly the duality of the two cones. And so for us, it's enough to convert the bonds to the extreme rays. But if the EFT without the C2 symmetries, we know that the bonds are more difficult to be obtained analytically. We can write a general form of the extreme array here with a constraint C squared larger than AB. We can make the variable substitution with the R, S, and W, which can remove this constraint, but this will make the problem become a quartic problem. And I want to remind you that from this formula to get the bounds is a non-trivial problem and we related to the Hilbert system problems, but eventually we can find the bounds. Here is the bounds, and we can see they are very complicated. Although the problem have to be solved, we still worry. If the numbers of the field is larger than 2, then the problem, we believe it will more difficult to be solved analytically. So for considering this, we are going to come up with two numerical approaches. Both of them can be achieved by the semi-definite programming. And the next, I'm going to introduce them. The first is the Monte Carlo approach, by which you can randomly search the extreme array in the spectral hadron. We can start with a random point X, and then we find its phase. Then I will take a straight line across it and find the intersection with the cone. If the new phase contains the new point is not dimension 1, then we need to take the iteration and go back to the step 2. But if the new phase is dimension 1, then we say we find an extreme array. Okay, if the bounds are finite, then we say we can take the large enough numbers of the random points to get the all bounds. But if the bounds are not finite, then we say we at least can get a set of the Monte Carlo sampling. The next approach is the Sdp approach, by which we can judge whether amplitude in M is in the cone or not. The programming will seek the minimal value Q dot M in the spectral hadron. So if the minimal value is not a negative value, then we say the amplitude should be allowed by the positivities. We know this approach is better than its elastic approach because it is solvable within the polynomial time complexity, but the elastic approach is an NP-hard problem. And our approach can also guarantee that our bounds are accurate. And based on the above approaches, we can mention several examples briefly. Since we know the Monte Carlo approach can deal with large problems, so but as an illustration, we can study a foreground case, which will contain about 16 fields. And this process will receive not only the contribution from the dimension A operators, but also from the double insertion of the dimension 6 operators. So we can numerically find the following bounds. In here, we find the number is large, and we take around 10,000 random points to get them. These bounds we can show that these bounds are consistent with the analytical results, and the bounds also shows that allowed version coefficient space is a 7-dimension polyhedron cone with about 48 faces. And we can also prove only a few of them can be obtained by the elastic approach. The next example, we are going to consider the stem model flavor setters, which will contain the E, mu, and tau. The positivity bound of these setters have been obtained by this paper using the elastic approach. We here can write the four fermion operators in dimension A in this. And we can use these operators to calculate the amplitude, and we find there are about 21 independent version coefficients. And if we vary one operators at a time while keep the other operators fixed at the red point, and the red point is manually selected, then we can find the elastic bounds and the exact bounds individually. We can see in this figure that our exact bounds are always stronger than the elastic bounds. If we pick up two of them to form a 2-dimensional parameter space, where the elastic bound have shows that the flavor violating effects will set a lower bound on the flavor conserving effects. And our Sdp approach have shows that we improve the elastic bounds. The third example, we are going to consider the famous DRGT massive gravity series. This will contain only one massive graviton, means that the series will contain 5 independent modes. So by the proper choice of the parameters, we can find there are only 2 independent parameters, C3 and D5. So in this 2-dimensional parameter space, the elastic bound have already been obtained by the famous paper using the elastic approach. We can use the Sdp approach to get the exact bounds. And we see in these figures, although it is just a small range, we indeed improve the minimum value of the D5s with the exact bounds. Finally, we come to the summary. Since that we know the positive structure will arise as the dimension A version coefficient space, it is a consequence of the axiomatic QFT principle. And the realistic problems will often involve multi-field EFTs. In this situation, our convex geometry perspective will help to understand these structures better. Here, in this talk, we have converted the problem of finding the extremal the bounds to a geometry problems, which is to find the extremal rays of the spectrum hadron. If the problem contains a small numbers of fields, then it can be solved analytically. But it contains a large number of fields, then it can be solved by the semi-definite programming. And based on this approach, we have improved several previous results, but we also gave some new results. So thank you for your listening.
Thanks a lot for the very nice talk. Do you have questions from the room?
So I have a quite naive question. So what motivates you think about the dual space instead of original Wilson that amplitude space?
Can you repeat?
Oh yeah. So basically, my question is that because you can also do it in the amplitude space, right? In that figure. Okay. But why do you do it in the dual space? So is there any advantage of doing it in the dual space instead of original amplitude space?
Yes. And in the dual space, because if the series have no symmetries, we know that it's very hard to deal with the bounds in the amplitude space, because we cannot get the CG coefficients to construct the projectors, then we cannot get the bounds directly. But if we use the dual space, the spectrum hadron is a well-defined object, so we can use a lot of the mathematical methods to get the bounds. I think it's very convenient because in our examples we have have good use with it.
So if the series have a lot of symmetries, so you can still use the dual space, right, to do it?
I think yes, because we have deal with the gluon case. We have the gluon case. We have the S3 cross S3 symmetries. We can deal with it.
Thanks.
Okay. Questions on the Zoom? Anyone? I don't see any. All right, then let's thank Xu again.
Okay, thank you.
Thanks.